What's up guys, my name is Brandon and today I'm going to introduce you to specific heat and heat capacity. So before I get started, I wanted to give you guys an example that would help you on the intuitive level what heat capacity is. So imagine that you're in the blistering cold and you're freezing to death and somebody comes up to you and they have two jugs. One is filled with hot water and the other one is filled with hot air. Which one do you choose to keep warm? If you guess correctly, you would choose the jug filled with hot water. And the reason why is because more thermal energy is stored in a jug filled with hot water than a jug filled with hot air. This essentially is what we're trying to understand, the quantity of thermal energy that's associated with raising or lowering the temperature of an object. This is known as heat capacity. We commonly denote heat capacity with a capital C. That's usually found in physics as well as chemistry. Mathematically speaking, we can express this in terms of calculus variables. So we say that dq is equal to c dt, where dq is our change in energy. That is equal to c, our heat capacity, times dt, which is our change in temperature. So that means that c is equal to dq by dt, or the change in energy with respect to temperature. So heat capacity is actually a very flexible quantity. We can measure it per mass, per volume, per weight, per object, per anything that you can really come up with as long as you're consistent with your measurements. So with these types of distinguishments, scientists call particular ones special names. So the heat capacity per mole of a substance is known as the molar heat capacity. The heat capacity per mass of a substance is known as the specific heat capacity, or for short, just specific heat. That one is just referred to with the lowercase letter c instead. So we reach kind of a snag when we're trying to understand gases though. For example, let's say I have a container that's filled with a gas and I hold the volume constant. If I raise or lower the temperature, then the pressure inside will also begin to increase or decrease. Or if I let the pressure be constant and I raise and lower my temperature, then the volume will begin to expand or contract. So measuring the heat capacity becomes kind of difficult for scientists because it depends on how we're adjusting our system or how we keep our system. So we decided to create two heat capacities for gases. There's heat capacity at constant volume and heat capacity at constant pressure. So for the heat capacity at constant volume, that's equal to the partial derivative of the thermal energy with respect to temperature held at constant volume. For the heat capacity at constant pressure, that's equal to the partial derivative of the thermal energy with respect to temperature held at constant pressure. Alright, so now on to our example. So we have two objects, okay? One is at temperature T1 with heat capacity C1, and the other one is at temperature T2 with heat capacity C2. We put these objects together and we allow them to undergo thermalization. Thermalization is any process that reaches thermal equilibrium. So all we're saying is that we put them together and they reach the same temperature. So they want us to develop an expression that represents the final temperature in terms of T1, T2, C1, and C2. So the way we solve this is by using conservation of energy. If I multiply a change in temperature by the heat capacity, then I get the change in energy. So whatever energy is lost by the object has to be equal to the energy gained by the other object. So expressing this mathematically, C1 times T final minus T1 has to be equal to the negative of C2 times T final minus T2. Once we have it in that expression, then we just solve for the final temperature, and that is equal to C1 times T1 plus C2 times T2, all divided by C1 plus C2. And so now you guys have learned about specific heat and heat capacity. Thank you very much for watching my video, and if you enjoyed it, please subscribe.